Okay, good morning, everyone. Can you hear my voice and can you see the black box testing screen on your monitors? Okay. Well, let's start then. Today's subject of discussion is the black box testing. As you remember, we have discussed last week software testing chapter, and in this chapter we have grouped the idea of testing into two: black box testing and white box testing, and we further pointed out that the black box testing is a functionality testing, and it doesn't require the code. No code should be available. It is not necessarily needed. And the white box testing, on the other hand, is a structural testing where we definitely need the source code or the code in general. Okay, let's start with the discussion. Black box testing is can be imagined using this diagram here. Here, our program is a black box. This black box tells us that we don't actually see the code. So it is for us only an executable. Okay, this executable, this program is given an input X, and whenever it is presented an input X, it provides an output f of X. So this is how we should see the program or the software product that we are testing. So that means we know for each input X what output f of X the program is supposed to provide us with. This here is a decision structure where f of X is the output that the program provides, and Y is the output that it is supposed to provide. So Y is the desired or correct output, and f of X is the actual output that our software product gives us. Well, we compare the actual output with the desired output, and if they're equal, then we're okay. Then there is no problem. At least for the specific test case, this program we assume passed the test. Otherwise, if they're not equal, then this points out a failure. That means we have to check out to see what is going on. We have to debug it, etc. Well, what is the correct output? How are we going to learn this? Where are we going to take this from? Our reference for the correct output is the software specification document. So we perform the functionality testing or black box testing against the specification document. Okay, any questions about this diagram? This diagram is important from the viewpoint that we understand the black box testing, or that we start to understand the black box testing. Do you have any questions on that diagram? Okay, then I pass to the next slide. What are the principles of the functionality testing or black box testing? It, as I said in the previous slide, it is based upon, or it is referenced by, the specifications and documents. So requirements, technical plans and architectures, user manuals, design documents, etc. The code is not necessarily needed. It is not required. But of course, that we have it definitely helps us further. Because I mean, to support the test, we may use the code, but the code is not necessarily needed in performing a functionality testing or a black box testing. The general strategy is that it applies especially to integration testing, system testing, and acceptance testing. So these are okay. Well, it doesn't okay. What testing is not mentioned here? Which one is the testing that is not mentioned in among these tests? Can someone write me from the chat panel? Which testing is the testing type which is not mentioned in the among these tests? Can someone make any suggestion? Okay, I'm waiting for someone to make a suggestion about which testing type is missing among these tests. Well, someone, if you can remember from the V model development what test plans are done, and then with what test type the testing starts. Which one is the first type of testing that we use to examine the software? It is the unit testing, right? Unit testing. So unit testing, the name of the unit testing is not mentioned here. Why do you think is that? Why is, well, of course, unit testing is also can also be examined by the functionality testing, but it is not mentioned here. Well, the best types of tests that we should apply functionality testing or black box testing to are the integration testing, system testing, and acceptance testing. Why do you think is that so? Why is the unit testing not mentioned here? Why are these testing best fit for the functionality testing? I mentioned that in our discussion in the last week, because this black box testing is the functionality testing. So we define the functionality of system, its subsystems, or possibly its modules. But, well, these modules, of course, should be large. As you remember, if you remember, we said that the separation, how the question or the answer to the question, how we separate, how we differ or distinguish the modules from the subsystems, is that the modules by themselves don't have a meaningful standalone functions. Okay, the modules of course have functions, but by summing up these functions, we obtain a meaningful function from subsystems, all right? So that's why when we make a functionality testing, we should rather apply this to uh, at least subsystems or to the system itself. But modules or units by themselves, since they don't have any meaningful function, meaningful standalone function, it's not really this black box testing is not really a good idea to apply to units. Integration testing, another thing is that integration testing, system testing, and acceptance testing, these are rather big bodies of code. So that means structurally, to test them structurally, to apply white box testing to them is usually not feasible because they contain code of very large sizes. Okay, so please keep that in mind. Black box testing is fit for integration testing, system testing, and acceptance testing, and the reasons are because these have meaningful standalone functions. That means subsystems or system or the system itself has have meaningful standalone functions. That's why functionality testing for it is good. And also to structurally test subsystems or systems becomes infeasible because they contain two big bodies of code. Okay. Another principle of black box testing is that it can be assisted by a post-white box testing phase to obtain code coverage measures as indicators of testing quality. Okay, so to assess, to measure the testing quality of the black box testing, we can use later, after the black box testing is done, a post-white box testing phase, so that by the code coverage measures, the quality of the black box test is assessed. All right. Well, let's talk about the basic idea, the main idea of black box testing, the domain partitioning. What is domain partitioning? What is equivalence classes? Let's talk about that. Well, we have to assume that we have inputs for the software product that we want to test. Let's come here and see X. Okay, this X represents the set of inputs that is to be accepted by the software product that we're going to test. Okay, so the domain, by domain, we mean this input set of the software product. Okay, the set of all input values that that may be presented to the software product we're testing. So that we call system domain. System domain is just like the function domain, for example. We want to know if we have a function f, and if we want to analyze this, use this function f of x, then we want to know its set of input, right? This we call domain. X is an input, and it is a member of a of a set of inputs that we call domain, and the outputs of this function we call range. Okay, so now just like a function domain, we have here the system domain, and it contains all input values that may be represented, I'm sorry, that may be presented to the software product. Okay. Now, equivalence class is a certain set of input values, a subset of domain or a subdomain, and well, let's go to this picture. Each of these we call an equivalence class, and the entire thing here, which is composed of both valid inputs and invalid or illegal inputs, we call the domain of the system or software product. Now, what are the equivalence classes? Why are these separated, and why does, for example, these inputs constitute or form an equivalence class? Well, let's go to this slide. Each equivalence class or each EC represents a central property of system, that is, each value in an equivalence class makes the system behave in the same manner. Well, any of these points in this equivalence class, for example, any of these points, if you present any of them into your software product, it performs it, or it behaves in some way. And this is true, this behavior type is true for all of these input points, right? Any of these inputs, whenever presented to the software product, these make the software product behave in the same manner. So that's why these input instances, these input points perform an equivalence class. Do you understand this idea? Do you have any questions on that? Any questions? Please, if you have any questions on what equivalence class means, or what domain, system domain means, please write from your chat panel. Okay. Did you understand, one more time, did you understand why black box testing well applies to integration testing, system testing, and acceptance testing? And why is the name of unit testing not among these tests? Do you understand that? Okay, well, you have no questions, so I assume that you understand. Okay, I continue with the equivalence classes. In testing, well, that the equivalence class means a group of inputs that makes the software product behave in the same fashion. Then in testing, each value reveals a failure or makes the system behave okay. So each value activates almost the same execution path through the system. Well, this remark relates the black box testing with the structure of the software product, with the code of the software product. Okay, each value activates almost the same execution path through the system. All right. So you can, in other words, you can also say that each equivalence class makes or activates or stimulates almost the same execution path or the same code pieces through the system. Well, equivalence class is based upon the system specification and it is based upon the experience and intuition of the tester. The quality of the black box testing is dependent upon the experience and intuition of the tester, and system specification document is document that is referenced by the black box testing. So do you understand? Do you have any questions on equivalence classes? Okay. Well, let's see the black box testing hypothesis. What is the black box testing hypothesis, and how should we understand it? Each value in an equivalence class results in correct execution or failure when used as input to system. Again, each value in an equivalence class results in either correct execution or failure when used as input or fed or presented as input to the system. So that means, or that implies, that for testing purposes, one representative input value from each equivalence class should be enough. What did we say about equivalence classes? That each of these points, when presented to the system, makes the system behave in the same manner. So that means, or that implies, that feeding the system with only one of these inputs is enough for the entire equivalence class to test the software system. Okay, so that is the black box testing hypothesis. For testing purposes, one representative input value from each equivalence class is enough. Well, this is theoretically so, but in practice, the hypothesis does not hold universally. So what does that mean? That means what we should deduce from that is that system shall be tested with several input values from each equivalence classes. Okay, so do you understand that? This black box testing hypothesis. Theoretically, one representative input for each equivalence class is enough to test the system's behavior for that equivalence class. But in practice, this hypothesis does not hold universally. So what we should do, we should test the system with several inputs from each equivalence classes. Do you understand that, ladies and gentlemen? Okay, I'm asking you all to let me know whether or not you understand from your chat panel. Say yes, we understand, or yes, we understand, or we don't understand. Please write that, each of you guys or ladies, write that from your chat panel right now, so I can see them explicitly. Okay, perfect. Okay, Tolga and Farg, thank you for your comment. Please, would you write from your chat panel, or do you want me to open up your voices, unmute you so that you can? Do you have specific questions? What don't you understand? Okay, Tolga, I unmuted you, for example. What is the specific thing that you don't understand?
I missed the previous lecture and I'm trying to understand, but
so you don't have any specific questions, is that right?
no.
Well, you should know that this is not totally dependent upon this previous week's lecture. Okay, it has some roots on this previous week's lecture, but it mostly an independent subject of discussion. Okay.
Okay.
So if you have any specific questions, please don't hesitate to ask me from your chat panel, or I can also unmute you. All right. Okay. Thank you. And uh, okay, you have the same reasoning. No, I just missed some lectures. Okay, all right, okay. If you do have any specific questions, please don't hesitate to ask them. Thank you, thank you. All right. Well, since you don't have any questions, I skip to the next slide. Jump to the next slide. All right, now let's look at this slide. This slide has some black dots. In each equivalence class, we have a black dot. So each black dot here represents the equivalence class it is within. So these black dots are the representative input points for the relevant equivalent class, for the equivalence class it is located in. Testing the code using a black dot will result either in a failure or it will pass this test and represent theoretically the entire equivalence class. All right. And as you see, of course, we have also a representative input for the invalid or illegal input set. So black dots are representatives. All right. Now let's see how we should form equivalence classes. So again, to be able to sum up and see the big picture here, we are constructing a testing algorithm. Okay, we are constructing an algorithm, or we are constructing a method for testing or for performing functionality test, a functionality test on a software product. We are here discussing what kind of a method we should construct to perform a functionality test for a software product. All right. So for this, we have mentioned, or we have defined a system domain, and we have further described that the system domain is composed of equivalence classes. All right. We have defined the system domain as the set of inputs that may be presented, legal or illegal, or valid or invalid. All input values that may be presented to the software product is within the system domain, should be considered in the system domain, and we should knowing that, now we have to form equivalence classes, that is sets of input values that once presented to the system makes the system behave in the same fashion, in the same manner. So now we are starting from this slide, we are discussing how we form these equivalence classes, or what the details are, what the important points are for forming these equivalence classes. For example, to specify a range of values, what we need to do, the corresponding, what type of equivalence class we need to form is, we have to form one valid and two invalid classes of inputs, right? Let's take as an example a an interval of an integer interval between the specific integers a and b. All right, and they are inclusive. So the input values may contain a and or b. All right. So what do we need to do to test the software product for such a range of values between a and b, inclusively a and b? So we have to create one valid set, one valid equivalence class, and two invalid equivalence class. So where should be these, or what should be these valid and invalid equivalence classes? Valid equivalence class should be an integer x between the a and b inclusively, and invalid equivalence classes, one should be less than a, and the other equivalence class should be from the set of integers that are greater than b. All right, and so that means for this range of values between a and b, we should use three values, three representative inputs. One for those numbers, those integers, I am sorry, that are less than a. Another one, a valid one. This is an invalid one, the one that is less than a. A valid one should be between a and b. And the third representative should be another one, another invalid one. It should be greater than b. So if you do this, then you formed the equivalence classes for this range of values correctly. Well, let's look at another alternative. So we want to specify a specific value within a range. Well, what should be the corresponding equivalence classes? And again, one valid and two invalid classes. All right. So let's look at the example here. A value of integer x shall be t. Well, this here is a specific value within a range. Value of integer x shall be t. So x here is the variable. You can imagine like that. X is a variable and its value should be t. So what are the valid and invalid classes? The valid one is, of course, where x is equal to t, the value t. You test the program for the value t, and then you test the value. The two invalid classes are those that are less than t, where you assign a value x to from a set which is less than t, and then you in the second invalid class you assign a value to x that is greater than t. So these are the two invalid classes here, and this here is the valid class, but the valid class here only contains one single value, because the definition of this value is that it should be equal to t. So the only valid class, I'm sorry, the valid class only contains one value and it is equal to t. All right. Do you have any questions here? Do you have any questions on this slide? Okay. Well, we continue with how we form equivalence classes. Well, we want to form an equivalence class for a set of values now. Okay, do you understand what we're trying to do again for this slide and now in the second slide? Do you understand what we're trying to do? We're trying to form equivalence classes, all right? And we form the equivalence classes for a range of values, for a specific value within a range, and now as a third alternative, we may form an equivalence class for a set of values. then what should we do? We should now form one valid and one invalid classes. And what should these contain, these equivalence classes? Well, those that are within a set one valid, that means we should form an equivalence class that should contain members of this set of values, and one invalid class that should contain members that are not members of the set of values. All right. So let's look at this third example for this. Well, our set of values is this one: two-dimensional geometric shapes that shall have four corners. Two-dimensional geometric shape, that shall have four corners. What are the valid, what is a valid equivalence class? It may be a square, it is composed of squares, rectangles, trapezoids, parallelograms, etc. These each have, each of these geometric shapes have four corners. So these are all within the valid equivalence class. Now let's look at those shapes that are not within this set of values: ellipsoid, circle, triangle, pentagon, hexagon, heptagon, etc. So these are 2D. These are 2D geometric shapes which don't have four corners. So that's why they are the members of the invalid equivalence class. Okay. Do you understand that? Do you have any questions on this third example? Please let me know from your chat panel if you have any questions. Okay. Well, then I continue. Well, what to do to specify a Boolean value? How am I gonna specify a Boolean value with what equivalence classes? Again, one valid and one invalid equivalence class will I use to specify a Boolean value. An example is here: x shall be true. Valid equivalence class is that x is equal to true, and invalid equivalence class is x is equal to false. All right. Now let's look at this. One or more equivalence classes for illegal values. That is to say, values incompatible with the type of the input parameter and therefore out of parameters domain. Example here is integer values x, illegal EC, real number x, illegal equivalence class character string x. So these are two examples to illegal values, equivalence classes that contain illegal values. All right. So if x is an integer, then two possible equivalence classes that represent illegal values should be, for example, real number x or character string x. How many equivalence classes? As many as potential groups of values. Okay. Well, this question is actually a question that describes how should we divide the system domain, that is the input set of the software product, into groups. How many groups should we form so that this input, this set of inputs of the software product is correctly divided into meaningful classes, right? So the question to that is, as many as the potential groups of values that are believed to be handled by the system in different ways. So if, for example, we have infinitely many input values, all right? Infinitely many input. Well, theoretically, of course, infinitely many input values, but all these input values, we think, we believe, may make the software system behave in, for example, 4 different ways. Okay, then how many equivalence classes should be there to represent all to for us to divide these input values? 4 equivalence classes, right? Why? Because among out of all these infinitely many input values, we can extract only 4 different ways the system behaves. All right. So that means we have to extract 4 equivalence classes. That is what this first remark tells us. Any EC shall be further divided into subclasses if there is reason to believe values in different subclasses are not processed by the system identically. So this here tells us further that if we have after, like for example, in my oral example, I said that if infinitely many, assume that we have infinitely many inputs to be presented to the system. But we know that, or we believe that, these infinitely many input values may make the system behave only in 4 different ways, right? Then we perform 4 different equivalence classes. But then later, after these 4 equivalence classes have been formed, if we have further reason to believe that, for example, in the first equivalence class, we have groups of values that that we started to believe that make the system in 2 different ways. Then we can further divide this first equivalence class into 2. All right. So you can form equivalence classes as you know in the as you believe in the process, in the testing process, that there are some input values that are further that form further a specific group. Right. Well, let's look at the boundary analysis now. Here, what we do is we said that theoretically the hypothesis, the black box testing hypothesis is for each equivalence class we have to specify or determine a representative input, and when we test the software product with or with the system with that representative input, then it should be enough for the whole equivalence class. But then we said that this is theoretically true, but in practice that doesn't hold. So we have to select several input points to test for each equivalence class. All right. Now in this slide, we are talking about what should be these representative inputs for each input class. And here we underline the importance of the boundary values within the equivalence classes. EC boundaries are where bugs critically show up. That's why boundary conditions are subject to test. So each black dot represents a boundary condition of its relevant EC it is within. So assume that, for example, one of these is the representative input, for example, let's say this one, and these are the boundary values for that equivalence class. All right. So that makes, for example, for this equivalence class, 3 representative input. 1 typical representative input, and 2 the boundary values. And this is true for each equivalence class in the system domain. Okay. Now, do you have any questions from the boundary analysis, from the equivalence classes, or from the black box testing in general? Do you have any classes? Okay, so if any questions, then I can unmute you so that you can talk. You can also talk if you find it difficult to ask questions in English. Please ask your questions in Turkish. I'm ready to hear questions if you have any. Please don't miss these sessions without understanding anything as much as possible. Okay, so okay. Okay, then. Please ask questions after whenever you have any. Ask questions through my email, through other media. Please don't pass these questions undetected. All right. Please learn whatever you don't understand. Don't hesitate to ask questions. Okay. I will see you tomorrow at 8:30 if you don't have any questions, and I will now stop this session. Okay, goodbye then.